Let ABC be a triangle with AC is greater than BC. Let omega be the circumcircle of ABC, and let R be its radius. Point P is chosen on AC such that BC equals CP, and point S is the foot of the perpendicular from P to AB. Ray BP meets omega again at point D. Point Q is chosen on line SP such that PQ is R, the circumradius, and SP and Q lie on the line in that order. Finally, let E be a point satisfying AE is perpendicular to CQ, so these two lines are perpendicular here, and BE is perpendicular to DQ. Prove that E lies on omega, the circumcircle of ABC. So how do we get started on this problem? Well, we have this random circumradius thrown in here, so let's try dealing with that. So we want to try looking at properties of point Q because that seems to be the main issue inside our problem. So, and if we take a closer look at things, we might, since we have a circumradius, we're inspired to try looking at lengths and distances between Q and other points. So PQ is equal to R. So what else could equal R? And looking at the diagram a bit further, we conjecture that QC and QD are both equal to R. So in particular, we conjecture that QD is equal to QP is equal to QC is equal to R. And in particular, that implies that Q is the circumcenter of triangle DPC. So how do we go about proving this? Well, if Q was a circumcenter, then the circumradius of DPC would just be R. So let's try proving that first, so at least we can get somewhere. So what is the best way to find the circumradius of a triangle? Well, we just use a law of sines. So in particular, we have that the circumradius is equal to PC over 2 sine angle PDC by the extended law of sines. And we want to show that this is the circumradius of ABC. And now let's take a look at what we have in our information given. We have that BC is equal to CP, and we haven't used that yet, so let's try using it. Then this gives BC over 2 sine angle PDC is equal to R. And therefore, the circumradius of DPC is equal to R. And we're doing this here because PD and B are collinear. Right. So now we just have to show that PQ passes through the circumcenter, at which point we will be done, because PQ equals R immediately pinpoints where Q is. Now here's where we use the fact that Q lies on line SP. And recall that SP is perpendicular to AB, as is shown here. So, and we want to show that this perpendicular line from P to AB passes through the circumcenter of triangle PCD. So, and now here's where we use, now we know that ABCD is cyclic. So, and we now have some special properties about cyclic quadrilaterals coming into play here. So first, per se, the angle bisector is fixed when we change the angle bisector of APB and CPD are the same. And then if we draw in this altitude here, so let's let this be that, then these two lines here are reflections across this angle bisector because this quadrilateral here is cyclic. And that means that this line PQ is just a reflection of this altitude here across the angle bisector. However, the reflection of the altitude across the angle bisector is known to pass through the circumcenter because, well, H and O, where H is the orthocenter and O is the circumcenter in any given triangle, are orthogonal conjugates. So that means that PQ indeed does pass through the circumcenter, and thus Q is the circumcenter of CPD. Now that we have that the circumcenter of DPC is Q and the circumradius is R, it just makes sense to draw in this circle. So here's what we do. So we draw in this part, and then the rest of the circle. And then it's a circle of radius R, and we already drawn in the center Q. So let's draw in the center of the other circle with radius R, which is just a circle. So let's go ahead and draw in the circumcenter O. So then we look at O and Q, and they're two centers of the two circles with the same radii. So that means that they're reflections of each other across the common chord. Let's go ahead and draw in the common chord again. So then, since O, Q, and Q are reflections across the common chord, this implies that DOCQ is a rhombus. So, and this circle is just making things a bit more messy, so we can erase that, but not erase O because now we know it's important, because we have the rhombus. So, there we go. So, and from our rhombus here, we note that DQ is parallel to OC, and similarly, CQ is parallel to DO. So thus, we reduce the condition for E such that AE is perpendicular to DO. So let me go ahead and write that down. AE is perpendicular to DO. And then for a CQ, it is BE is perpendicular to CO. And because we have our perpendicular bisector here, because CO is perpendicular to BE and OB equals OE, that implies that BC is equal to CE if E were to lie on omega, and also that AD is equal to DE. So these are true if E lies on omega. And if we add the two, then we get AD plus BC, the arcs, is equal to the arc CE plus DE, which is just the arc CD. So if we can prove that this is true on the circle omega, then we are set because that will show that the point E actually exists. We have now reduced the problem into showing that the sum of this arc here plus the sum of this arc here, where all the arcs are minor here, and at least in this diagram, is equal to the arc CD. So, and in terms of angles, this equates to angle ABD plus angle, and then we have angle B something C. So suppose BAC, because that's simplest, is equal to CD, and the only lines which have both C something and something D is just this point B. So we have CBD. So we'd ideally like to show that this is true. So let's try looking at this left-hand side here. So we have that ABD is this angle here, and BAC is this angle here. So by the sum of the angles in the triangle, the sum of these two angles here is 180 degrees minus this angle here. And 180 minus that angle is just this angle. So this angle plus this angle is equal to this angle. So now we just have to show that this angle here is equal to angle CBD, which is just this. However, now we use BC equals CP again, because now BCP is an isosceles triangle. So that means that these two angles here are equal. And we are done. We have solved 2023 IMO Shortlist Problem G2 using angle chasing and the law of sines. Thank you so much for watching this video. Please subscribe if you'd like to see more problems from the shortlist.